Now let's look at road surveying. Position for the road survey is important so that features of the road can be reported. Position accuracy of 1 meter or better is normally demanded, as this gives a clear indication of which lane the problems are in. It also enables features on the road can be monitored accurately. For 1 meter positioning, differential corrections are required. Operating radios over a large area is hard, so services like OmniStar or beacon transmissions are required. Post-processing is important, but this can be costly. If the data is available in real time and can be put in directly into the customer's databases, then there is no need to waste additional time post-processing the data. Now let's look at a road surveying example. To test the accuracy of the RT systems for surveying applications, we drove down a motorway. We repeated the route many times, always using the same lane. The graphs on the following pages plot the lateral error of the RT on each route. The distance along the motorway is about 12 kilometers. Now let's look at the road surveying SPS. This graph shows the lateral error of the RT using a standard positioning service non-differential. There are 9 drives down the M40 on the graph. The table gives the RMS position error and a standard deviation for each run. The difference between the RMS and the standard differentiation is the average error along the whole route. Now let's look at the road surveying with the RT beacon. This is the same test, but using the RT beacon to provide differential corrections. The error is substantially less than the standard positioning service. Now let's look at the road surveying OmniStar VPS. Using OmniStar, the lateral error is even smaller. The system has a specification of 1 meter 95% or 50 centimeters CEP. In practice, we achieve results that are closer to 50 centimeters 95% using the OmniStar VPS. Remember that the error here has both the OmniStar error and the driver error in it. Let's continue looking at the road surveying. In this graph, we see one of the passes with raw data included. The spikes represent places where there are bridges. There are gaps in the GPS data under the bridges. The RT is able to reject the spikes and is able to smooth the GPS measurement. The standard deviation of the GPS measurements is 0.85 meters, about twice that of the RT. Although the accuracy of the RT is the same as the GPS for open sky measurements, it is more accurate when there are obstructions. At a bridge, we can see the jumps in the GPS position. This is probably caused by fewer satellites and problems tracking the carrier wave close to the bridge. Note the difference in scale of the two axes. The vertical grids are spaced at 2 meters and the horizontal spaced at 1 meter. The size of the GPS jumps are about 1 centimeter around the bridge. This data set uses differential corrections from the RT beacon. We have found that the jumps without differential corrections are larger.